So we're now in 3.4, library functions, piecewise functions, and in this section we're going to kind of introduce the idea of graphing functions and then get into piecewise functions, and then we'll kind of in a couple of sections get back to these idea of functions, graphing functions, transforming functions, moving them around. Now, for the very first starting graph in this section, there's a lot of very good strategies to graphing, and we will cover these good strategies. But one of kind of the staples of graphing, and this is a strategy that I still use in my graduate courses. So we take this function, and then we kind of just guess values for x, and then find the result for y. And so there's ways that you can pick these in a clever way, and there's ways that you can pick them poorly. Generally, a good strategy is to have two negative numbers, 0 is always really good to plug in if you can, and two positive numbers. And sure, the more points you get, the better idea that you're going to have with your graph. And sure, you could probably guess your graph sometimes with 2 points if it's a line, which I don't really recommend depending on that, because we don't see that many lines in this course. That's not true. So we're going to move into this strategy of graphing with a table. And so the strategy is just guess and check. Take some values, plug them into our equation, and find the results for y. And there's ways we can pick these numbers. Randomly, I know what this graph looks like, so I kind of cheated on the numbers that I picked. But in practice, you pick random x's and find out what their y value is. So a good idea or a good kind of starting place is to pick 5 points, 2 negative, 0, and 2 positive. The more points, the better. I would recommend doing at least 3. If you have any less than 3, there's a good shot you won't have a good idea of what your picture will look like. So I picked -8. Plug in -8 into my function. The cube root of -8 is -2. Great, that's a point. I can definitely plot that, and I will shortly. Plug in -1 for x. Cube root of -1 is -1, so I get that. Same thing with 0. I plug in 0. Cube root of 0 is 0. Now, sometimes I pick points, and let's say I just pick 2. Well, the cube root of 2 is 1.26, and I could potentially graph it if I had like a graphing program, but if I'm doing this by hand, that's not a very helpful point, and that's perfectly fine. If that's the case, just move on and don't really plot the point, or maybe pick a different value to plug in. Like in this case, +1 would have been better than +2, but that happens. That's completely normal. When you're graphing things, sometimes the point that you pick isn't the most helpful, and just kind of work around that. And then I picked 8. Cube root of 8 is +2. So as I mentioned, when I'm making this graph, I could plot 2, 1.26. I didn't, and I don't really need it in order to kind of get the picture of what this looks like. Now, I have a bit of an advantage because I've seen what the cube root of x graph looks like, but if you try to make a graph by connecting all of these points, the chances are you'll have something pretty similar to the correct answer, which is this. And so that's when we have these things in our toolbox that make it so that graphing is much easier. It's nice to have the general idea of what the shape of a cube root of x looks like, because we take a little bit of the guessing game out of it and know, okay, I have a graph, it's going to go through these points. I know what cube root of x's generally look like, and so this has to be the graph. There isn't really much many other possibilities that it could be. Okay, piecewise functions. Now this is a difficult concept. If I had to kind of pick the top 3 concepts that people struggle with in this course, I would put piecewise functions among them. And it's kind of weird, but what a piecewise function is, there should be an equal sign next to the f of x. Anyways, what a piecewise function is it saying, okay, it's all well and good if I have a really nice parent function that says it's just x squared, and that's it. But in the real world, when you're modeling situations, that's not going to happen. Like, even if we think about a simple case, punting a football, yeah, a parabola is a really good thing that would model the projection of the actual ball, the height and the distance from the kicker. But then as soon as it hits the ground, it stops being a parabola anymore and it rolls for a while. And so to account for that, what we sometimes have to do is we have to have a piecewise function, which says, cool, what's happening for the first part, every time x, everything that's less than -6 is going to be, my graph's going to be 3x. But that's not the entirety of my graph. And so in between -6 and 3, my graph will be 2x squared. And then everything bigger than 3, my x will be equal to -2. So it's breaking a function, that's the name, into different pieces, and then specifically saying, this is when I'm going to use that function. So for starters, if we're just going to evaluate, we want to find f of -7, well, I look at what my input is. My input is -7, and now I look at where that would fall. I look at the right side of the equation, not the left side yet. And so I look at my inequalities. Well, -7 is less than -6. So I'm going to use that function when I'm evaluating. And so now I've picked which piece of my function I'm going to use. I'm going to use my 3x, and then I'm going to plug -7 in for that. Evaluate, I get -21. To see it again, f of 0, okay, well, I look up at my function. What section does that fall into? It falls into between -6 and 3. 0. So now I'm using the middle function. I plug in 0 for x, I solve. I get 2 times 0 squared. Well, 0 squared, 0. 2 times 0 is 0, and I have my answer. Finally, now f of 3. Now this one's a little bit tricky. So this one doesn't really fall into any of the regions per se. Like, it's not between any of the two numbers. It's not bigger than any of the numbers. And so I have to look and say, okay, f of 3, my input is 3. Which category does this fall into? Which piece does it fall into? And I have my middle inequality is x is less than 3. My bottom of the inequality is x is greater than or equal to 3. Well, I say, okay, well, 3 is equal to 3. So this is actually going to fall into my third case. It's greater than or equal to 3. And then to make this a little bit more confusing, is this function is actually just a number. It's -2. So when I go to evaluate my function, well, I plug 3 into the function. I can't plug 3 into anything. It's just going to be -2. So my answer is -2. Kind of to hammer that concept home. Let's say I wanted to find f of 10. Well, plug in 10 to f of x is equal to -2. X isn't there anywhere, so it's going to be -2. Well, what's f of 100? -2. What's f of 1000? -2. So anytime you have a constant value, it doesn't really matter what your input is. I mean, it does with a piecewise, so you can figure out which function you're going to use. But when you've decided what function you're going to use, if it's a number, doesn't matter what you're plugging in. It's always going to be that number. Okay, graphing piecewise functions. It's a little bit tricky. If you kind of see a piecewise function just straight up, like, let's actually show you one. Like that. That might be a little bit overwhelming because it doesn't seem like anything you may have seen before. But really, actually, what's happening is that they are all graphs that you have seen before. In fact, very recently. They're just torn up into pieces. Like the first graph, that's a parent function. The second part between 1 and 2 is a parent function. And the third part, 2, 1 on, is a parent function. So when we're trying to graph something, we're going to have to go piece by piece. And so we start to graph this function by looking at the very first part of the function, x plus 2. Now, if you haven't graphed lines in a while, it'd probably be a good idea to review that. But what's happening for this first equation is that my slope is 1, so that'll be up 1 and over 1, and my y-intercept is 2. So if I'm going to graph that line, not worrying about whether or not it's a piecewise function, that's just the graph of f of x is equal to x plus 2. Now, since it is a piecewise function, now it's be a good time to start using a pencil in the course if you're not doing that already. I'm going to erase the right side of the graph because I only want this to be my graph for when x is less than 0. So I erase the right side. I take everything less than 0, and notice how it's not like less than 0 vertically wise. It's less than 0 as in x is less than 0, so the left side of 0. And then since it's less than 0 strictly, I'm going to put an open circle on 0. If I'm going to graph 2, f of x is equal to 2, that's just a horizontal line. And now I'm going to erase everything less than 0 and everything greater than 2, because my piecewise function just is going to exist in between those two values of x. And I'm going to put a closed dot on 0 and an open dot on 2. And since that left corner is just a single closed dot, sometimes people don't even put a dot there anymore. They just leave it as though it's connected. Either way is fine. I would give you full points. Now for the last part, same idea. I'm going to graph just the line, negative 2x plus 5. So that has a y-intercept of 5 and a slope of negative 2. That's what this graph looks like. And then I want all of the values for x is greater than or equal to 2. So I want only the stuff that is to the right of x is equal to 2. So I erase all of those left values. And then I put a closed dot on 2. And then that is my graph. That's my piecewise function. To reiterate it, that would be kind of hard to, if you just saw it, say, oh, okay, like, yeah, I know how to graph it. That's something I've seen before, because it's not. It's a bunch of pieces of things you've seen before. So it's much easier to go spot by spot, kind of get rid of the parts that you don't care about, and then at the end of the day, you will have a graph of all of the pieces. You will have a piecewise graph. Now, to go in reverse, again, as I already mentioned when I started the last slide, this is a hard graph to look at and say, oh, obviously the equation is going to be this. Instead, go part by part. So I'm looking at my graph. I see kind of that left side looks like it's following one continuous movement. So I'm going to look at that part and say, okay, what does that look like? And I'm going to imagine that I continue that instead of stopping at the dot. If I don't see it yet, I'm going to continue that line for a while. Well, that's a parent function. That's the x squared graph. So I know it's going to be f of x is equal to x squared, and then the only other thing I have to talk about is when I would be drawing that graph, or for what values of x am I drawing that graph. Well, I'm drawing that graph for everything less than or equal to 1. So my first equation, x squared, x is less than or equal to 1. And we're building to a piecewise function. So this is actually not going to be part of my final answer, but it's kind of part of the scratch work that will get me there. Well, the next piece that I see is kind of that floating horizontal line. Horizontal line, that makes me think of another parent function. Horizontal lines are just a number. In this case, it's 3. So if you couldn't see it, you could just extend your line and see, okay, it hits y is equal to 3. So f of x is going to be 3 for that line. And then I just have to describe when that line's happening. It's happening for all the values greater than 1, all of the values less than or equal to 2. So that's f of x is equal to 3, and there's my interval. Now the last part of the graph is a line. And in this case, it's pretty seeable what the y-intercept is, but that's not always going to be the case. So if you have a line that's not like a nice, neat horizontal line, I recommend just extending it all the way until you hit the y-axis. Like that. Oh, okay. Well, when I extend it that way, I see that it hits 0. So my y-intercept of that line is 0. And looking at the line, it goes up 1 over 1, up 1 over 1. So I need to draw the line, write the equation of a line with the slope of 1 and a y-intercept of 0. That's f of x is equal to x. Then we ask ourselves, what values of x is that happening on? It's happening everything bigger than 2. So x is greater than 2. Now, to kind of put it all together in that nice notation, we only want a single f of x, and then we want to kind of use that curly bracket and put everything together. So f of x is equal to, I put all 3 of my equations, I put all 3 of their associated intervals, and that's my final answer.